Okay. Good morning, everyone. Welcome back. I hope you had a good spring break. So, all right, to get started, do you have any questions before we continue where we left off since last time? Yeah, sure. Yeah, that's sure. Okay, so yep. So we, so the highlight, of course, right before the break was, well, we were kind of still discussing chapter 11 and the first few sections at that. And the idea, right, is, well, confidence intervals, right, for some parameter. And we focus so far on the mean, by the way, but, right, so the idea, right, is that we have sample depending on theta, right? And what we want to look for, right, is we want to construct 1 minus alpha confidence interval for theta, meaning, right, that something of this form to statistics that depends on the sample, so that the probability, right, that theta is in this interval, right, is 1 minus alpha. Okay. And so the idea for construction is basically we want to find the pivot, right? Pivot stat for theta. And from the pivot stat for theta, we will pivot right around that statistic and we'll obtain the left point and right point of the interval. Classical example, of course, right? So it's easier to look at an example when we have IID, normal mu sigma square. And we remark, right, that, we don't necessarily know what the pivot stat is right off the bat. Usually we know the estimator, right, for the, so here we want a confidence interval for mu, right? 1 minus alpha confidence interval for mu. Okay, and let's assume that both are unknowns. So we start out with the estimator for mu, and then we normalize, right? We want to normalize this estimator to obtain the pivot stat. And the normalization step may or may not be that obvious, right? Depending on right how much we assume that are unknown and how much we know about the distribution of the statistics that are involved. So here, right, we discussed how this follow a Tn-1 distribution. And so, well, I guess to remind you too, right, the reason is, of course, that x bar minus mu divided by sigma over root n, right, is standard normal, and n-1 s square, right, over sigma square is a chi-square n-1, and these two guys are independent. So therefore, right, when you form the ratio, right, when you form the ratio of z divided by square root of chi-square n-1 divided by n-1, that would be Tn-1 by the definition of a T distribution. So, right, so all of these knowledge goes into construction of the pivot stat. But after we obtain the pivot stat, then the act of pivoting, or the act of constructing the confidence interval is pretty straightforward, where we just write down, right? For example, this is minus Tn minus 1 alpha over 2 less than Tn minus 1 alpha over 2 is 1 minus alpha. This is true by definition. This is just the quantiles. And so pivoting means, right, of obviously isolating the mu and then put everything else, right, on the other on the two hand sides to obtain the left point and the right point. And so what we got, of course, is that, right, x bar minus Tn minus 1 alpha over 2 s over root n plus alpha over 2 s over root n is 1 minus alpha. And so we obtain, right, the confidence interval for mu in this case, right? So of course, this is a quick review of confidence interval for the mean in the one sample case, but also kind of a review of the idea of the pivot statistics technique. Do you have any questions here? Okay, so that was 11.1, 11.2. So for 11.3, we want to look at confidence interval for differences in mean. Okay, and so the context is something like this. We have x1 up to xn 1, right? IID, normal mu1 sigma 1 square, and let's call this x like superscript 1, right? This first sample. The second sample will also be normal with potentially, right, different means and different variances. So here, right, without any assumption, okay, without any assumption, we should assume that none of these are equal, meaning like mu1 is not equal to mu2, these are not equal, sample sizes don't have to be equal. Of course, right, the, I guess, quote, confusing part is you will see later on that some of the times we assume some of these parameters are equal to make our results easy. But those are specialized cases, and you should understand the motivation on why we make those assumptions, right? But the most general structure, we don't have to make any assumptions yet. And so, especially for the mu1, mu2, right? So the theme here right now is that mu1, mu2 are unknown, and we want to find the confidence interval, right? 1 minus alpha confidence interval for mu1 minus mu2. Okay, so how do we do that? So, and obviously we start out with the easy case where we assume that sigma 1, sigma 2 are known. Okay, and again, this is highly artificial, it's not practical, but we make this assumption to demonstrate the point, to explore the idea before we remove it. So first, right, we want this. So we want the estimator for this. Obviously, the estimator for mu1 minus mu2 is mu1 hat minus mu2 hat, which is x bar 1 minus x bar 2. And we should recognize, right, that by itself, x bar 1 minus x bar 2 is a normal. Oh, so we should also say, right, that these two samples are independent of each other, which is important. So these two samples, right, among themselves are independent. For example, let's say I sample the height, right, of the male students at Rutgers, and I sample the height of the female students at Rutgers. So, right, these two samples are independent of each other in that way. So x bar 1 minus x bar 2, because these two samples are independent of each other, we'll have a normal with mean mu1 minus mu2 and variance sigma 1 square over n1 plus sigma 2 square over n2. And so because, right, this depends on this parameter, I mean, well, it's not normalized, so it's not a pivot stat. So the pivot stat in this case, because sigma 1 and sigma 2 are assumed known, will be x bar 1 minus x bar 2 divided by square root of sigma 1 square over n1 plus sigma 2 square over n2. And this will be standard normal. And so therefore, the confidence interval is straightforward. X bar 1 minus x bar 2 plus or minus z alpha over 2 square root of sigma 1 square over n1 plus sigma 2 square over n2. All right, and so that was where we left off last time. Any questions here? All right, so the main point, of course, is when sigma 1, sigma 2 are unknown, right? That's the most important. Oh, you know what? Thanks, Christine. That's excellent. I definitely, because this by itself, right? Thank you. It does not have, right, mean 0. Thank you. Yes, yes, that's definitely a mistake. I forgot to subtract the mean. Thank you very much. Yes, thank you. Okay, so, but this is still correct. I mean, I just know it on top of my head, but yeah, I wrote this wrong. So when sigma 1 and sigma 2 are unknown, right, what do we do? Well, so, I mean, roughly speaking, intuitively, right? So obviously, the question is, what is the pivot stat? Right? And roughly speaking, everyone knows that somehow it has to do with replacing, right? This unknown parameter with their estimators. But, okay, but there are a lot of times, right? This is actually the point of this class, and you'll see this same idea happened in, you know, all your other stat courses, except that it's not done as explicitly or as carefully. The point is that replacing this is easy, okay? Everyone with some basic knowledge of stat would know that. The hard thing is to decide what the exact distribution is after you replace, okay? In other words, right, to have the pivot stat properly, as I mentioned before, you need to know exactly what the distribution of the pivot stat is. So it's not enough for us to say, this is what we want. If you just say, this is our pivot stat, that's really just half of the equation. The other half is the t distribution, okay? And that's why the t distribution has a name, right? I mean, the first person to publish this got, you know, I mean, well known for that. The reason, again, is because without knowing this is useless in some way. I mean, not useless, but it's not precise. So let's see, right? And let me demonstrate that here, the situation becomes more complex because this is a pivot stat before. Let us, you know, kind of blindly, right? Just replace sigma 1 with S1 and sigma 2 with S2. Okay. So question, what kind of distribution is this? Is it T? Is it Z? Is it something else? Do we know? Good guess, but F will come later. F will have to do with ratio of 2 chi-square. The top definitely is not a chi-square because the top cannot be, the top is not always positive, right? The top is clearly some kind of normal coming from here. So no, right. And all kind of, guesses in the, area. Yes, you all have some idea, except that all this is wrong. Okay, and this is exactly where it's hard. I guess Madaf and Derek both have a point, right? But so Madaf, right? What you said is wrong, is because what you did not, what you're dividing by here is not constant. Correct, exactly. Yes, right. That's exactly it. Because the whole point is exactly that these are unknown. All right. So it's not constant, therefore, right, it cannot be exactly standard normal. What Derek said is wrong is because it's a little more subtle, and that's exactly the point here. That, well, what does it take to have a T, right? To have a T distribution, you must have standard normal. Where was it? Standard normal divided by some kind of square root of chi-square. Okay, do we have that here? It looks like we have it here because, right, the top is some kind of normal, already mean is 0, right? But the variance is not 1 because, right, we need that. So in other words, basically the top, to make it into standard normal, we need this. Okay, so this is the act of normalization. On the other hand, on the bottom, right, which is this whole thing, do you see any chi-square happening? Do you see any chi-square happening? And by the way, right, let's not forget that to transition from here to here, somehow you have to compensate by the same factor at the bottom. So in other words, it's not, I'm not freely writing this division. I'm writing these divisions kind of provisionally so that at the bottom I have to compensate by this to begin with. But we'll talk about that later, right? The fact is, do you see any chi-square happening at the bottom? Well, let us just kind of, do a wishful thinking, okay? And see what would it take to have a, yes, Aaron, but we don't have that, right? You're guessing that's the target. That's what we would really want to have, except that do we have it here, right? Because to have it, right, remember that you must have something like n1 minus 1 s1 square over sigma 1, right? And then n2 minus 1 s2 square over sigma 2 square. This is our wish for target. Right? Yeah, right. Oh, you all kind of see what I'm getting to, except, right, the subtle point here is, do you see somehow, and is there any algebraic operation for us to come from here to here? Or let's even forget this, right? Let's forget this for now. Let's stare at this. Is this a pivot stat? Can I use this as a pivot stat? right? So forget this for now. Let's stare at this. Can I use this as a pivot stat? Because why can't I use it as a pivot stat? It is normalized, right? It is normalized. Right. I mean, the fact that we don't know mu is fine, okay? Because mu will be the one that we will pivot away from, right? Right here, for example, you see, the fact that mu1 and mu2 are unknown are fine here. Actually, we need it because that will be used as pivot, right? Right here. To look at this example, you see, mu is unknown here, right? But that's fine because that's exactly what we isolate. What Christine pointed out is correct, that exactly here, I used sigma 1, sigma 2 to construct my pivot stat, right? Exactly that is used normalized, right, Madhav? So it is normalized because I'm normalizing it here. This is standard normal. This is chi-square n1. This is chi-square n2, right? The whole trouble here is that I use these guys to construct, to normalize, and they stick, okay? They stick. They do not cancel. So the answer is no, because it involves unknown sigma 1, sigma 2. Okay? A little bit subtle, but get this point. Mu1, mu2 are fine because that's what we want. The unknown part are sigma 1, sigma 2, which is not fine. Normalize is fine because I did normalize it. Any question here? So let me go back to, right, the one sample case and show you why, right? At one point I did mention it's a very beautiful procedure, but I guess you did not quite appreciate, right, why it's beautiful. Let's go, let's see that again. In the one sample case, right, I have x bar minus mu divided by sigma over root n on top, right? That's what standard normal. At the bottom, I need square root of n minus 1 s square divided by sigma square. That's for chi-square. But I also do a 1 over n minus 1 because, you know, it's chi-square n minus 1 over n minus 1. So why was this fine as a pivot? Why was this fine as a pivot stat? Why could we use it in the one sample case? But when we move to the two sample case and try to generalize it, it doesn't work. Exactly, the sigma cancel out. So even though it's used in the normalization procedure, is there as just, you know, a placeholder, right? It cancels out. Okay, that's the whole point. That's what makes it work here, and that's exactly what does not make it work here, because these two guys do not cancel. That's the main point. Are we okay here? All right. So now let's then ask the question, motivated from this question, right? And clearly we need to do something like this anyway, because, right, there's no way we can go back to this guy, right? There's no way we can go back to this guy because sigma 1, sigma 2 are unknown. So right here, what can we do? What can we do to make sigma 1, sigma 2 cancel here? What can we do to make sigma 1, sigma 2 cancel here? Well, the answer may surprise you. We make a very interesting assumption. We say sigma 1 and sigma 2 are equal. If sigma 1 and sigma 2 are equal, you see that this will exactly cancel out. Okay? And hence, you see that that is going to be a very popular assumption in the comparison of sample means, that they assume that the two samples have the same sigma. All right? But without understanding the motivation, I think a lot of us will just say, well, we assume that we carry out our business, things work. No, right? That at some point you see is a quite strange assumption, but it's motivated at least at some level on, right, being able to derive the exact statistic, okay? The exact distribution of our pivot statistic. So we make the extra assumption. Okay, then, right, you see that so maybe, right, let's remember this. This guy, right, will be n1 minus 1 s1 square over sigma square, right, plus n2 minus 1 s2 square over sigma square, right? Well, clearly, it's just n1 minus 1 s1 square plus n2 minus 1 s2 square, right, over sigma square. Because now the sigma square have the same denominator. Because of this, right, I mean, so at some point, this is just the same denominator we want on top. But this motivates us to look at one extra statistic that pops out from this context. That if you define as p square to be n1 minus 1 s1 square and 2 minus 1 s2 square divided by n1 plus n2 minus 2. Oh, and by the way, right, so let's backtrack a little bit. What distribution does this one have? What distribution does this one have? Correct, chi-square n1, right, minus 1. Chi-square n2 minus 1. This should look very familiar, right? This is exactly your midterm question. So if you add this and they're independent, then this one would be chi-square n1 plus n2 minus 2. And you see where this comes from then, right? This comes from that. Or another way to say this is, right, you have two samples. How many data points do you have? You have n1 plus n2 data points. To come up with this statistic, right? By the way, this is, right, the name SP square is very obvious. It's the pool estimator for the sample variance. So this is nothing but sigma hat square, the pool estimate, right? Okay. So this object, right, pops out exactly from this consideration. And what do I want to say here? So the n1 plus n2 minus 2, right, can be motivated from just exactly look at the chi-square sum. Or if you want to look at it from another angle, which is equally interesting and very statistical, is that you have n1 plus n2 data points. To come up with this estimator, you need to estimate two parameters. In other words, the mu1 and mu2, because it costs you 2 degrees of freedom to estimate, mu hat 1, which is x bar 1, mu hat 2, which is x bar 2, in sp square, right? You see, it's not exhibited explicitly out here for you, but s1 square, what is it? It's a sum, right? xi minus x bar 1, right? Square over n1 minus 1. So like that. So right here, right, to construct s1 square, you need x bar 1. To construct s2 square, you need x bar 2. Everything else is known. So it costs you 2 degrees of freedom from that point of view, right? Anyway, so this pool estimator object, right, this pool variance estimate is exactly what show up in the denominator if we assume that the sample variances, if we assume that the population variances are the same, right? Sigma 1 squared equals sigma 2 squared. So you see that our pivot stat now becomes x bar 1 minus x bar 2 minus mu1 minus mu2 divided by, right, sigma square times square root of, sorry, not sigma square, just sigma 1 over n1 plus 1 over n2 divided by, right, square root of sp square n1 plus n2 minus 2 divided by sigma square times 1 over n1 plus n2 minus 2. This is our pivot stat, right? And it comes from roughly almost kind of mimicking this, just some extra normalization to make sure that this is a chi-square divided by its degree of freedom, okay? So these two I wrote down here are motivations for you to think of how, right? This is like a thought process where you move from here to here to construct your pivot stat, and you realize some difficulty. So you make extra assumption, and eventually this is your final product, right? This is the right pivot stat. Why, right? It has the following, right, desirable properties of a pivot stat. First of all, it does not depend on any unknown parameter, right? The sigma cancel. Again, right, the mu1 minus mu2 is there because we are constructing confidence interval for it. The distribution of this would clearly be standard normal divided by square root of chi-square n1 plus n2 minus 2 divided by n1 plus n2 minus 2. So it will be a t n1 plus n2 minus 2. Is this okay? So the confidence interval, right? 1 minus alpha confidence interval for mu1 minus mu2. Again, right, assuming sigma 1 square equals to sigma 2 square equals to sigma square. I mean, we don't need that because it doesn't show up explicitly. Is x bar 1 minus x bar 2 plus minus t n1 plus n2 minus 2 alpha over 2 times sp, right, divided by, times sp square root of 1 over n1 plus 1 over n2. Is this okay? Any question on any of this? So some things, right? For example, I mean, I don't know if this is a point of confusion for you, but when I don't pay attention, when I first saw this stuff, right? This object right here always kind of tripped me, because I wonder, shouldn't that be something like, I don't know, 1 over n1 square, or I don't know what it is, 1 over n1 plus n2 square, that kind of thing, right? Just again, of course, right? Why not something like this, for example? Square root, whatever, right? Why something like this? I mean, I don't know if I'm asking some obvious question here, but you know where this comes from, right? This, for example. Does the question make sense, or is it too easy? Where does this factor come from? Exactly. It's come from the variance of x bar. That's it, right? It comes from the variance of this guy. So you see the entire construction of the confidence interval is just about the variance in some way. So if you don't need to remember, right? Sorry. Is exactly that, right? Or rather, you see, it's really sigma 1 square over n1, sigma 2 square over n2, but because they are the same, you factor out, right? So that's why when you normalize, right, you take the standard deviation, you take the square root. Okay. So these things, for example, you know where the structure comes from. Then you can just put the pieces together. You see that right there, SP stands for sigma. This goes right here. This is just the quantile. Question? All right. So you mean here? Yeah. It's an okay question, actually. It's not bad. So first of all, right, a lot of these things, I mean, it's kind of, sad that we don't get to do data. But, like a class, is a class, is too many things to do if you have to do data. But let me ask you this, right? Unit is something that someone who does this kind of thing should be kind of always keeping in the back of their mind, just in case questions like this come up. So let's suppose that, remember, like we say this is height, right? So let's say this feet, just say that, forget the inches, right? Just say feet. Then suppose that we look at height, then this x bar, what's the unit of x bar? Feet, right? Feet, no unit, no unit. What's the unit of SP square? Or what's the unit of S square? Remember the construction of S square, right? Something like x minus x square divided by something. So the unit of S square will be feet square. So you definitely, when you have a confidence interval for feet, right, you cannot have feet square in it, right? Even from unit point of view, that just makes no sense, right? So standard deviation always have the same unit, right, as the measurement of whatever the experiment. Variance, right, has the unit of the measurement square. So variance is the object that's easy to calculate, but right, the unit you use is always standard deviation, right? When you have your exam back, you do not want me to tell you the variance, because the variance is not in the same unit as the score, right? The variance has unit of point square. So that's one way to answer your question. Another way, of course, is that, look at this. The normalization here, right, is by standard deviation, exactly for the same motivation. So here you have SP rather than SP squared. Yeah. Any other question? So one more thing, right? This is kind of dial back to chapter 8 on estimators, or is it chapter 10? Chapter 10 estimators. So whenever you have some estimators, right, it should make you pause and think a little bit, even though it's not the point of the question, right? The point of the question is confidence interval. But you see that in this context, you have 3 candidates, right? In the context, right? This is just a side remark, really, but it's interesting by itself. Suppose you have, so in this context, right? In this assumption, you have 3 estimators for sigma square, right? S1 square, S2 square, SP square. Agree? Where obviously the motivation is S1 square is you ignore the sample 2, you just do sample 1. S2 square, right, you ignore first sample. SP square, you pull the 2 samples together, right? And by the way, this is the definition, right? You pull the information together. Well, you know, your boss will tell you, I don't know, you're the statistician, compare them for me. How are they, you know, compared? What would you say? Anything you can say about these? Excellent, Aaron. That's exactly what I want to hear. That's exactly it, right? All unbiased. So from unbiased point of view, they're all the same. All right. SP square is the most efficient. SP square is the most efficient. That actually explains why you want to do a pool. And then, you know, Aaron just more down to earth, right? He said this is lower variance. That's exactly it. You all use fancier language. You say it's low variance. Okay. And that's the whole point of pool variance. I mean, from estimating point of view, right? You have 2 samples with the same information. You pool them together, you get a better estimator. Okay, so I'll say that Aaron is right on the track. All unbiased. SP square is most efficient. By the way, is there any comparison of efficiency between S1 square and S2 square? Any comparison between S1 square and S2 square in terms of efficiency? Right, exactly. That's exactly right on target. But now, can you go further a little bit? Make your own assumption. What would you say? suppose you're free to make your assumption. Can you say something more? So correct, exactly. That perfect. So yeah, what you can say is the one with the higher sample size will be more efficient. You don't know what it is because you don't know the actual sample size, but if you do know, then the one with higher sample size will be more efficient. And again, you see that exactly also the same reason why SP square is most efficient, because in pool, right, it has the most sample size within it. Okay. So I won't go into the calculation, right? I hope that you can more or less see where these calculations are based on. These are not just, right, waving hand. We can exactly prove this point. I'll leave it for you to take care of that. Okay, any questions left? All right. So this is all I think what the book says about comparison of the mean of two samples. But I want to mention one of this one additional case that's not in the text, I think. Okay. But I think it's very popular. Okay, so I want to mention it. It's called pair sample. I will put a question mark here. As far as I know, to the best of my knowledge, it's not there. But you know, the book, our book, your text, has a great habit of sometimes hiding the interesting part in the problems. So they might have mentioned in the problem that I somehow missed when I browse through. But definitely they do not cover this in the main discussion. Okay. So what would pair samples look like? So for convenience, let me just say this. You have x1 up to xn IID. And for the sake of discussion, I can even throw in normal, doesn't matter. And for the sake of discussion, I can even throw in well, let me just do it like this. And I have y, okay? So, but here, right? Let me tell you that xi and yi. So notice here that with pair samples, you always have that the sample sizes are the same, they're paired. So in other words, si and yi are related in some way. Okay, where do you see this? Well, you see this in a lot, actually in a lot of before after experiment. So for example, you can say that they are for example, so they are kind of like the blood pressure of patient I before and after, receiving some treatment. Right. So suppose that you have there's some medication for blood pressure that the pharmaceutical company would like to test out. So they would give measure blood pressure before and after, right? The patient takes this treatment, and obviously I guess the target is that, right, somehow show that mu2 is less than mu1, right? Blood pressure is lower. So anyway, right, I mean, we're not going to go into the whole point of that experiment, which is for our question, right? We just want to do something like this. Let's say mu1 minus mu2. Okay, like that. Now, for the sake of discussion, let me just say, even assume, right, that sigma 1 square equal to sigma 2 square equal to sigma square, right? So in this case, let me ask that, is the confidence interval going to be the same as what we put above? In other words, it's going to be something like this. So n1 plus n2 will be 2, right? Will this be the confidence interval in this case? Okay, yes, sure. Anyone else? Right. The fact is, right, in pair sample, the two samples, for that reason, are not necessarily independent. Right. And that's the whole point, because you see, this is the blood pressure of the same patient receiving the medication. So you can see, right, that okay, the medication does something, but how the blood pressure moves can also depend on, you know, the person's physical, right, kind of attributes from other, you know, points of view. So for that reason, right, the reading before and after, you don't have any basis to say they're independent. And by the way, right, in this calculation, for example, in this generic construction, where did we use independence of the sample? Where did we use independence of the sample, of the two samples in constructing this? Like in these objects, right? Which object depends on the independence assumption? Right here is one, right? Because if they're not independent, you need the covariance term. And even right here, this is chi-square, all right. This is chi-square, all right. But because these two guys are not necessarily independent, when you add them, it's questionable whatever that object is. Okay, it's not, you don't know it's chi-square. So in other words, this whole construction does not work for pair sample. Okay, and so be careful on the independence assumption. I mean, if you work on many textbook problem, right? You're so used to the fact that two samples are independent, you don't even pay attention when you apply it to practice, right? Even in the easy case like this, the independence of the two samples must be questioned and cannot be assumed. All right, as far as I can say. So, any question here? So, right, the form we learned cannot be applied. So, what do we do here, right, for construction of mu1 minus mu2? So the right approach is to construct a third sample. You want the difference, right? Just construct the difference. So in other words, this means that, right, the pharmaceutical company goes in and measure the difference in the blood pressure of the same patient, right? I mean, of course, if they have this data, they can construct the difference. Then what is the distribution of ZI? So ZI, right, will be IID with normal, right, from our assumption, with mean mu1 minus mu2, some kind of variance, which we just call sigma square. Okay. So here, actually, the sigma 1 and sigma 2, right, will interact in some way that construct a sigma. And there's a covariance term that we assumed. Now, so from the assumption that these are IID sigma square, we make an extra assumption in a way that we say the covariance, right, the dependent structure between xi and yi are the same. In other words, there's some dependence between xi and yi, but we say the covariance is the same. The covariance dependence is the same between across patients, which again is a tall assumption, right? Because somehow, right, the person's reaction to the medication before and after across different patients may not be the same. But again, right, the more realistic you make, the harder, right, the construction you want to make. So here, right, I assume that somehow the interaction is the same. There is a dependence, but the dependence is the same across different patients. So I'm just addressing the independence assumption, right? I'm not addressing the homogeneity across different patients. But anyway, if you assume this, then the confidence interval, right, for mu1 minus mu2 would just be your standard one, which is z bar plus minus, right, z alpha over 2 s over root n. Let me do sz, right? I'm not sure if using this z confuses you. This is not normal, okay? This is just x, y, and z. If you want, I can change it to like a v or something to not confuse you. Is this okay? So this is what I want to mention, that in a pair sample, right, experiment, what our standard construction for the difference in the sample mean cannot be used. You must directly observe the difference among the samples and then construct the one, you know, sample variance, but just sample variance. SV square is, you're asking for the sample variance, right? It's just a standard one. So maybe let me do this, right? Sigma square V. But SV square is going to be, you know, VI, right, minus V bar sum square divided by n minus 1. Okay. As long as I have these guys are the same, then this should be the estimator of that. Yeah. So the point is, right, I'm not trying to make this too fancy. All I'm trying to say is, right, the independent among samples, right, assumption may not always hold. So, right, watch out for when that does not apply. For example, in this case, right? So a two sample problems, right, on the surface may have to be a kind of, you know, collapse back into a one sample problem, right? So in other words, the information contained in the sigma square V here is not the same as the information contained in the in SP, for example, because, right, when you do this, you do not take care of the covariance structure, how these xi and y are related. But here, because you already subtract them, it takes care of that covariance structure. Any question? Okay. So let's move on to 11.4. 11.4, the textbook calls it the estimation of proportions. But I want to call this asymptotic. Confidence interval, or we say that's another name for it. Walt type confidence interval. Okay. So, and this actually covers all the things we discussed so far and something we discuss in the future too. This is a concept about asymptotic confidence interval. So first, let's go back to what we discussed so far. So so far, right, we discussed that, let's say, roughly speaking, right, the confidence interval, right, for mu in one sample case would be something like this, right? It's going to be x bar plus minus, let's say z alpha over 2 sigma over root n, if sigma known, and then it's going to be x bar plus minus t n minus 1 alpha over 2 s over root n if sigma unknown. All right. Now, what do these constructions depend on? What do these constructions depend on? You see that they depend on, right? They both depend on normality, right? Normal population assumption. In other words, I must give you something like x1 up to xn, right? IID, normal mu sigma squared to begin with. If I were to give you something like x1 up to xn, IID, let's say exponential lambda, like your quiz, or right exponential uniform, right, 0 to alpha or whatever, right, 0 to beta, I forgot already, 0 to a, right, like your homework, then these constructions do not work. So do not apply, right? So these do not apply. For the obvious reason, right, that x bar here in this case, in these cases, do not have, right, the normal distribution, right? And if you want to construct it, right, correctly, then you have to derive somehow the pivot stat that relies on, right, somehow summing the exponentials or summing the uniforms, right, as you see on homework. Okay. So to construct the pivot stat, right, in here, or sorry, to compute the distribution, right, to compute the distribution of the pivot stat, right, in the non-normal case, is I don't know, is involved, right, calculation wise. All right. So what one situation we can consider is that if sample size is large, all right, if n is large, So, but hold on, let me say this, right? On the other hand, in all these cases, for example, in these cases, you see, on the other hand, in the non-normal case, right? In the non-normal case, in the examples above, okay? The previous stat always involves X bar. Okay. For you go back and you see what you did on the homework, or what we did in the lecture for related to this homework, right? Somehow X bar shows up in the construction, right, of the confidence interval for these guys. So now, okay, and that's why I say, right, to compute the distribution of the pivot stat, meaning to know what X bar looks like, or some normalized version of X bar in this case, can be involved in calculation wise. But on the other hand, right, if we assume n is large, then X bar is approximately normal. Okay. So that gives rise to the idea of asymptotic, or Wald type. These are kind of same thing. When you hear Wald type, this is not mentioned in the book, but a lot of other statistical contexts or courses will tell you that this is a Wald type confidence interval. Basically, you use an approximation in the distribution of the pivot stat, like this. Okay. So if n is large, then it doesn't matter what the population distribution is. X bar, if you involve X bar, it will be approximately normal. And so we rely on that to construct asymptotic, right? So the asymptotic confidence interval for mu, right? And this is independent of the normal assumption. Relies on the fact that X bar minus mu divided by S over root n is approximately standard normal when n is large. Okay. Now, I want to say one thing. I want to show you how this is used, and then I will, go back and remark on this. But I want to say that, this is not your standard central limit theorem yet, because your standard normal central limit theorem would require this to be sigma, right, instead of S. So there's something a little bit subtle here as well, that I do not use sigma here, I use S, okay? But even if I use S, this is still approximate standard normal. So this is still good. I will go back and remark on this. But accepting this for now, okay? Like almost like central limit theorem. Let me show you how it's used. So how it's used is basically you just pivot, right? You just pivot using this statistic. So in other words, what we have is this. If we have x1 up to xn IID with mean mu, right, and variance sigma square. So I don't mention anything about the distribution. Then you can say that, right, when n is large, the 1 minus alpha approximate confidence interval for mu would be X bar plus or minus Z alpha over 2 S over root n. Okay. So several things to pay attention here. To pay attention to here. First of all, no distribution is assumed. Second, I require n is large. Third, this is an approximate confidence interval. What does that mean? What that means is this, that, in all of the above, when I mention any of this, right, this kind of confidence interval, is exactly that the probability that mu1 minus mu2, whatever that is, right, is in this interval is 1 minus alpha. Is exact, right? If you were to write down the probability that, mu1 minus mu2 is in this, is exactly 1 minus alpha. On the other hand, when you construct something like this, the probability that mu is in here can only be said that it's approximately 1 minus alpha. It's not exact, right? You don't know what the exact number is. Maybe a little bit more, maybe a little bit less, depends on the case. Okay, so that's what approximate means. Third, notice that even though I use S here, it's still Z, right? It's not a T, it's a Z, okay? And this actually trips people up in different ways. It trips people up in the way that in this asymptotic case, they still use T just to be careful, right? So even though n is large, and it's really the idea is to construct approximate confidence interval, they still use T. Okay, they still use T like this. They would do T n minus 1 alpha over 2. That's one thing that I've seen. Another one, this is not serious. If you use T here, it's not serious. Another one actually is more serious, is in the case where, like here, when they meant to construct exact confidence interval, they use Z. That's serious, okay? So here, replacing T with Z is serious. Here, replacing Z with T is not that serious. So maybe for that reason, right, people always use T when they see S, just to cover their ground. But all right, let me explain why. That, so first of all, right, using T here is not bad, but it's still, there's no call for it. And also it actually shows that you don't quite understand the problem. The reason why using T here is not too bad is because when n is large, the T distribution is close to a normal distribution. So whether you use Z or T here doesn't really matter, okay? But using T here in this particular scenario shows that you don't quite understand what's going on, is because the asymptotic confidence interval relies on this fact. And the answer here is a normal, it's not a T. So therefore, if you use a T here, that's not a serious problem in terms of your result. But the right result here is a normal, not a T. Using a T here, right, instead of using a normal here instead of a T is serious, because, right, when we do this exact confidence interval, we do not say whether the sample size is large or small. In other words, our results are meant to hold no matter what the sample size is, even when n equals to 2, right? I mean, n equals to 1 is not possible because you need at least 2 sample size, right? Two sample points to construct a variance. But even n equals to 2 or 3, this works. And at a level when n equals to 2 or 3, the T distribution is very different from the normal distribution. So if you replace Z here with the T here with Z, you make a serious mistake, okay? But the point here is, right, that you can just use Z because you're doing approximate confidence interval and because of this result. Any question? So I assume that's okay. So for example, right, that when you have x1 up to xn, let's say IID exponential lambda, then if n is large, then the 1 minus alpha confidence intervals for, sorry, let me say approximate, right? For lambda would be x bar plus minus z alpha over 2 s over root n. x1, xn, IID, Poisson lambda. Again, right, n is large, same. Well, wait, let me say this, right? N is large, 1 minus alpha approximate constant interval for lambda is also x bar plus minus c alpha over 2 s over root n. It gets so repetitive that somehow you just kind of think that this is universal. But this is where the danger is, right? It's not universal. You got to pay attention to what the context is. The reason why these are the same is because in both cases, right, the mean, right, is lambda. So that's why for this result, I get the same structure. Well, to show you something slightly different, right? For example, if x1, xn, let's say IID uniform 0 to a, right? Then if n is large, what's my 1 minus alpha confidence interval, approximate confidence interval for alpha? It would be 2x bar plus minus z alpha over 2 z alpha over 2, right? 2s over root n. Is that okay? The reason, right, is because here, alpha, right, is not the mean. Alpha is not the mean, right, of the uniform 0 to a. But obviously, when you do this, what are you saying? You're saying that alpha hat, right, a hat is 2x bar. A hat is 2x bar. Right. And so if x bar is approximately normal for when n is large, then clearly 2x bar is also approximately normal when n is large. So you can use this as an approximate confidence interval. But you have to modify it, right? Because now the estimator for alpha is not the mean. So it's not going to be x bar, but 2x bar. Is that okay? Now, finally, you have, let's say, x1 up to xn, IID, but now it's going to be Bernoulli P. Okay, Bernoulli. So here, P, right, is the mean, right? P, because expectation of any xi, right? Expectation of xi is equal to P. So P is the population mean in this case, okay? On the other hand, though, when n is large, so P is exactly the proportion that the textbook mentioned in 11.3. 11.4. The variance portion. Oh, nothing special there, Madhav. The reason, right, is because if it's 2x bar, what is the standard deviation, right? If y is 2x, how is the standard deviation of y compared to the standard deviation of x? Twice, right? Yeah. So that's why I put a 2 here. Everything else is the same. Yeah. All right. So, all right, sorry, quickly, let me write it, okay? So if n is large, this is the last thing I'll tell you, and then we'll pick up next time. The 1 minus alpha approximate confidence interval for P will be P hat, all right, plus or minus z alpha over 2 square root of p hat 1 minus p hat divided by n. All right. So there's something to be said here about this versus whatever we wrote above, because above what we wrote is S, okay, the sample variance. Here we say p hat 1 minus p hat. So p hat 1 minus p hat is not necessarily S squared. All right, but the standard one that people use for the proportion confidence interval is this. So there's some difference here that I want you to pay attention to. Okay, and then we're gonna kind of go into more details of this on Friday. All right, so that's all I have for today. Thank you guys for coming. I'll stay behind for questions. If not, I'll see you on Friday. You too. Thank you. You too. Thanks. You too.